So let's go ahead and get started, and I'd like to introduce to you one of the co-leads of the study that's running this week on single photon counting detectors, Professor Jonas Smutsnes.
Thanks, Michelle. Today we're fortunate to have a speaker, Daniel Prober from Yale University. Dan, as you can see, is a professor in the physics and applied physics departments at Yale. Dan was an undergraduate at Brandeis, and then from there went on to Harvard to do his PhD under the supervision of Mac Beasley and Michael Tinkham. For those of you who know a little bit about superconductivity, those are pretty famous names in our field. And then immediately after getting his PhD, went to Yale, and that's where he's been ever since. Dan has done work on a wide range of topics in superconductivity and in other areas of condensed matter physics. He's studied the inelastic processes involving electrons in superconductors, various types of superconducting detectors, including tunnel junction detectors of two kinds, direct detectors and heterodyne, as well as hot electron detectors. And in addition, other more fundamental physics measurements involving superconducting devices and materials. So we're very fortunate to have Dan here today. He's going to be telling us about single photon detectors from A to B.
Thank you, Jonas. I'm delighted to be here. It's an honor to speak at Caltech down the hill from JPL with people that I've collaborated and worked with and known their work of for over 30 years. I'm reminded of a time when, as a faculty member at Yale, I went back to my undergraduate alma mater, hadn't thought about mentioning this, and gave a speech, a general talk. They were doing a fundraising with a major donor to put an addition on their building, and they had a very nice dinner. And at the talk, I reminisced about my time as an undergraduate student. And I reminisced that there had been one professor who had really scared me to the point that when we saw him coming down the hall, I would duck into the telephone booth. In those days, we had telephone booths, and pretend I was making a telephone call. And the thing that I remember from that dinner is every faculty member in the front row was nodding that they were just as scared. Okay, so I don't think there's anything scary in this talk. How many people are here now but were not attending the workshop? Okay, so thank you for coming through the rain. The talk I'll give will have a little bit, or have some from what I spoke about at the workshop. We'll have some new things. I'll be talking about some of the fun of making the detectors, some of the challenges, especially the superconducting detectors, which I know much better than the semiconductor detectors. We had some very nice talks this afternoon about semiconductor, or at least non-superconducting detector development. And Dr. Nixad spoke, and if you want to find out the real expert's view, please speak to her. Are there any undergraduates in the audience? Well, I was going to give my pitch for attending graduate school at Yale. Would you pass that on, please? Okay. Now, let me start by saying that the reason we stopped at the letter B is biology is probably the biggest present application other than astronomy that I know about, or at least I know enough about. I've learned some from my colleagues at Yale about that, but I've learned a great deal and had some wonderful collaborations over my career with both Yale colleagues and colleagues outside, especially at the NASA labs and at Caltech. So I want to acknowledge that and actually thank the two workshop organizers and tell you some specific things. So for each of you, I have a Yale Applied Physics mug. And I'll say a word or two. Paul? Yes. So because the beaver is ambiguously a campus mascot, for those who understand that, you'll see why. I chose the JPL bear, which we happened to have at home when I took the picture. The two organizers, let me first talk about Paul, who in the late 1880s and early 1990s was a collaborator of ours when he was at University of Massachusetts, and we had some wonderful fun designing and building SIS heterodyne mixer receivers, which in those days was a very new venture for us. And part of that excitement was the outcomes of the science, but also I'd mentioned that the three people that worked at Yale, one of the graduate students went on to be a postdoc with Jonas. The other one went into superconductivity research, but when Westinghouse ended its laboratory studies of that, he went into analog circuit design, and he's now a manager. The fellow that worked with Jonas is a principal venture capitalist on Sand Hill Road in Palo Alto, and the postdoc is chairman of the microelectronics department at Chalmers University, which is as big as all of engineering at Yale. So I wish him well. He's a very calm individual. So thank you, Paul. Jonas has both received graduates from my group and sent in 1995 an exciting postdoctoral fellow, Rob Shulkoff. Rob subsequently joined our department in '98. He was our top choice, and there was no ambiguity about hiring someone who was already there. He's now the holder of an endowed chair in applied physics and engineering, and it is named for the Norton family, who were the early funders of engineering at Yale many years ago. And in particular, their family crest is represented by that little decoration on the mug. The other thing, and a small ad for graduate school at Yale, is the gears on that mug. As you can see, there are 3 gears. Those are in honor of and in recollection of the first PhD graduate from engineering at Yale. Does anyone offhand know that person's name? Tom? J. Willard Gibbs, a certainly reasonably eminent physicist, maybe the most eminent American physicist of that century. And for his PhD thesis, he did engineering, studied the optimal design of the teeth of gears. So that's the explanation for the mug. And thank you, gentlemen. Okay. The talk, I'll go to an outline. Briefly, I'll talk about some of the major types of devices, and we've heard a lot about all of them at this conference, and then talk about applications, and toward the end I'll talk about the more, I'd say, familiar applications in biology, and I think that's where many exciting future advances will occur. Let me go back here. The motivation for single photon detection is that we'd like to get every bit of information out of the photons that we can. In particular, the detectors that I'll be talking about often will allow us to measure the energy of the photon, and through the Planck relationship, E is the Planck constant times the frequency, we can measure the frequency or the wavelength and determine a lot about the system that's emitting the photons. Now, these are very sensitive detectors, therefore they can measure small energies of particles that impinge on them. And there are a number of challenges in the field, and I think the biggest challenge, which is now being successfully handled, is making large arrays of these detectors once the single pixels are understood and mastered. And the energy scales for the visible photons in the range of 1 electron volt, actually 1.6 to about 3, and for the longer wavelength, far infrared, is in the milli-electron volt energy range, and that's in the millimeter wavelength range. So first, I'd like to start with a demonstration and a gift for all of those who are attending. Anyone who comes in late, they're welcome to get their gift. May I have a volunteer from one of the graduate students? I guess most of us are graduate students at one point. Volunteer? And, oh, come on. You don't have to do anything other than distribute the special glasses. Okay, well, Jonas was once a graduate student, and this wasn't pre-planned, but he'll wear a special spectroscopy lab coat to help him in his distributions.
You can tell Dan grew up in the 60s.
Yes. And actually, you can just pass it out by rows, and I have more. And I will let me keep one.
See, this is proof that the grad students are smarter than professors.
As if we needed any proof. Okay, what these glasses will allow you to do is to look at white light and see that it's all full of colors. Now, you probably knew that, and you've probably demonstrated that in your classes, but it would be nice then for you to take these home, show your kids, show your friends, show your roommates, show your parents. I like to give them out to the freshmen that I teach so that they can tell their parents that they're getting some value for their $30-some thousand of tuition. Now, it's easy. You can just look up at the bright lights. If you look straight up, it's pretty. And in fact, what you're seeing there is the spreading out in different angles of the different wavelengths or the different frequencies. You got enough?
You're scary.
Okay. And I'd like to also show you, once everyone has their glasses, I have a white light, and I'd like to give this to Michelle when later. But the white light gives you the same effect. If you just look here, you can see it's nice and all the colors. Okay? Now, another thing I can do, and you can keep on the glasses, although it's not critical. Oh, no, keep on the glasses, is, as in the movie Men in Black, there's a flashy thing involved. And you can see the different colors, and they're separated by the diffraction grating glasses that you're wearing. So I gave it away. What you're using are diffraction gratings. They're actually transmission diffraction gratings, and there are two of them, crossed and X and Y. That's why you get the different orders of the spectra. Okay. Now, the last thing is, if I want to take a green, a monochromatic, a single color, single energy, and simply project it, I want to do it. I'm going to block the reflection because this is a very bright system. Is you can see that spectrum. And what I'll try to demonstrate, and this is a little bit kludgier, is two different colors and show that they're diffracted differently, although you already know that. I think this should work. So you can see that the red is more widely spaced than the green. There. Now, the central peak, the brightest one, they aren't aligned because I haven't, the lasers aren't exactly coincident, but the spacing for the red and the spacing for the green is different, and that's the diffraction effect. Okay, so you can put down your glasses. Now, why do I show this other than to have some fun and give you a souvenir? Well, the detectors that we'll be talking about don't do that. The detectors we'll talk about report some electrical quantity that's proportional to the photon energy. They're energy dispersive in that way, but they're not spatially dispersive. You could, in fact, combine a diffraction grating with one of the energy dispersive detectors. That's been discussed in this workshop. But in any case, this is a different way from measuring energy, and if there's sufficient energy resolution, sufficient accuracy of spreading things out, then the detector will be quite useful. Okay. So I'm going to turn down the lights. And we'll just go through the slides. Okay, so we've already seen this slide. as an introduction, the basic detector, or the simplest one we'll talk about, is a detector that measures heat or energy or power. In this case, a small block is heated up, and an attached thermometer reads the amount of temperature increase due to the absorption of a photon, or if it measures a power, a stream of photons. And if a single photon is absorbed, we use the resistive characteristic of a superconductor, which has zero resistance at low temperatures, a finite resistance at higher temperatures. This is called a transition edge sensor, and we sit somewhere on there to start, and when the photon is absorbed, the temperature goes up, the resistance goes up, and then it comes back down, as shown here. And the temperature rise is proportional to the photon energy, so for a linear slope, the resistance rise is proportional to the photon energy. That's how we measure the energy of the photon. That's what makes it energy resolving, and that is the basic operation. Okay, I'm sorry. And in a number of cases, I've borrowed slides and tried to give full attribution at the bottom. And if you see your slide and it's attributed to someone else, that someone else probably stole it from you. Okay. In any case, the readout of these devices could be with regular amplifiers at room temperature, but that's both inconvenient and not low enough noise. The preferred readout is, at present, a superconducting quantum interference device, which measures the magnetic field, and the way it works is the current flowing through the thermometer sensor changes when the resistance changes. That current flows through a coil which applies its magnetic field to the squid. The squid then is read out electrically, maybe in a complicated fashion, but the squid sits down at a low temperature, sometimes at the same temperature as the device. And therefore, you can have a lot of squids because they're not all that big. And a number of efficient schemes have been developed for multiplexing to allow maybe a certain number of squids to read out many, many more transition edge sensors, or at least with a certain number of output lines going to room temperature. And so structures as complex as the one I'll show you, this is a telescope on Mauna Kea mountain in Hawaii. The James Clerk Maxwell telescope has on it a detector array, and this is not for measuring single photons, but rather for measuring power, but it's a very important observational instrument called the submillimeter common use bolometer array. This is the second version, and in it there will be over 10,000 detectors, and using a structure similar to one I'll show you, and they measure the incident power using squid readouts. And a very nice size scale, and I showed this earlier as well. This is the apparatus that will go there. This is before it went. And this is Dr. Kent Irwin, who is one of the participants and lecturers in our workshop. So that gives you the size scale. Oh, previously, for those who were unfamiliar with radio astronomy, these are two vehicles down here to give you a size scale for how big the antenna is. And then going down to the device level, these are 3-inch wafers with many, many of the bolometer detectors. The structure is built on a block of silicon, which is etched all the way through, leaving just a thin membrane, about half a micron thick or so, of an insulating material, silicon nitride, and the thermometer, the transition edge sensor, sits underneath. Over here, the absorber, the thing that absorbs the photons, is not shown. This is for absorbing X-rays. It's optimized in its operation for that. And the speed of it is roughly millisecond time scale. So this is not for ultra-fast counting, but it's appropriate for the intended astronomical applications. These devices work very, very well they have performance that matches very closely the theoretical prediction based on a lot of careful understanding. The way they're tested is you send in single X-rays one at a time, actually from a radioactive source that's down in the cold environment. The cold environment in this case is about 100 millikelvin, so that's really cold. And the X-rays have an intensity versus energy, if you measure lots and lots of them, that fit this light blue curve. The measured data fit into bins that correspond to energy are the red crosses, and those crosses are fit by the black curve, which is approximately 2 electron volts wider than this blue curve. And so if you had an X-ray emission that was a very narrow line width, you could resolve it to approximately that accuracy. And you could, of course, tell the center of it very accurately if you have a large number of counts. And looking at the line shape of emitted X-ray lines is important in the astronomical application. So this is a real success in that it's gone to the point of being moderate scale integration. In this business, it's large scale integration. And it performs almost an order of magnitude better than the existing silicon diode detectors in terms of the energy resolution. Okay. There have been a number of other applications of these kinds of detectors. There will be one coming soon where these transition edge sensors will be put into measuring X-rays emitted in a plasma physics experiment, and that plasma physics experiment is actually relevant for developing understandings that are good for astrophysics. And this is work reported by Megan Eckhart. Another example, and this is, oh, and there are seats over on this side if you want, or, yeah, come down. This is a particle detector, not a photon detector, but it uses just the same principle. It uses a transition edge thermometer, but with an even larger absorber made out of a tin crystal coupled to the transition edge sensor. And this is being used in applications for nuclear safeguards and testing, nuclear medicine, and it's starting to be combined with commercial equipment so that this can be used in a number of laboratories. And here's a real picture. And for example, if you were looking at nuclear safeguards and you wanted to know how much americium versus plutonium of those particular isotopes, a silicon detector, which I think has about 8 kiloelectron volts energy width, would give you this answer. This is energy in kiloelectron volts, so this is millions of EV energy for the incident alpha particle. Both the NIST detector, which I think is the prototype of the one developed at Los Alamos, both give much better accuracy and allow a much more quantitative result. Now I'd like to turn to another kind of detector to show you the other ways of solving these challenges of photon detection. This is a detector that's been studied for many years and recently has shown promise, and some of the themes of this detector have then been used in a very successful new venture. This detector takes the photon energy and operates at very low temperatures where all the electrons are combined into units called Cooper pairs, which is what makes up the superconductivity state, what gives the superconductor its zero resistance, its superconduction. The energy then breaks these up, essentially breaking the binding energy of the pairs. And although initially one pair is broken, after things settle down relatively quickly, we're left with a large number of single electrons that came from breaking up pairs. And that number is roughly the photon energy divided by the binding energy of the pair. Okay. This single electron number can be detected if we extract it from the system by tunneling, let's say, from this superconductor to that one through a tunnel barrier. The charge that is extracted is the electron charge times the number of units that cross the tunnel barrier. And so by measuring the charge that tunnels, we can determine the energy of the photon. And in addition, there's relatively little uncertainty in that. The accuracy is roughly given by statistics of the production of these single electrons. And that statistical variation can be a part in 1,000 for the case of kilovolt, kiloelectron volt X-rays, although it's not typically as good as the transition edge sensors. This detector, unfortunately, does not have a convenient low temperature preamp available. Rather, it has a high impedance and uses a room temperature amplifier. That's limited the scale of integration to 100 or maybe a few hundred devices, just due to the complexity limits and patience of people that do these things. But it's been very useful. These detectors have been used as measuring devices in a number of synchrotron light sources. And this is a slide from researchers in Japan. The important thing here is that the energy resolution is very precise. That's actually achieved by a crystal monochromator. The detector is used to sort out different groups of lines, and so its energy resolution is not as, the demands on its energy resolution are not as great. I see a question.
Previous slide, what limits the spatial resolution of the, yeah, you've got 200 microns. Is there any limit to that, making it smaller?
It's easy to make it smaller. Usually for the X-ray detector business, you want to cover as large an area as you can, just to catch as many X-rays as you can. So in the next slide, where they have about 100 detectors, those are not for doing spatial imaging, it's just for having a larger collection area. Making it smaller actually makes it more sensitive. That would be okay. Making it larger eventually leads to a degradation of its energy resolution. So the 300 microns is a convenient upper limit, roughly speaking. Okay. And here's the apparatus in the Japanese lab. This is an apparatus developed by Dr. Stefan Friedrich, who's at Lawrence Livermore, and I'm proud to say a former student who worked on the physics of the devices when he was a graduate student with me. And again, the newer detector, this is a refrigerator that gets down to about 60 millikelvin, and the cryogenic part of it is extended out in this vacuum snout to bring it near to the source of the X-rays, so the collection angle, the collection fraction, is as large as possible. Okay, so these are in routine operation under computer control. The cryogenics is a little bit complex, but presently you can buy cryogenic systems that are completely without the need of pouring in any cryogenic fluids. They operate under computer control and are relatively simple, although they're not inexpensive. So this is a business where in the future the cryogenic aspect will be much more turnkey than it has been. It will not require a physicist to run it. That may be good or bad, but in any case, that will be the way it is. Now, there are also a number of sort of niche applications in astronomy and other areas. This is a picture from the European Space Agency of a distributed readout imaging device, and each strip here is an absorber of X-rays, and the single electron charge is collected from this end and that end for the strip. If the X-ray hits in the center, the charge divides equally. If the X-ray hits on one side, the charge is more collected at the closer end, and so the total charge that's collected tells you the energy. That's the idea of these detectors, but the ratio of the charge tells you where the X-ray hit, and so you can do spatial imaging using just two amplifiers. And so this has 60 of those strips, 120 amplifiers, and will be put on a telescope by colleagues in the European Space Agency. Okay. Now recently being about 7 years ago, there was a wonderful advance in this field, and this was done here in Pasadena. the idea is called the Microwave Kinetic Inductance Detector. The acronym is MKID. And the concept uses the same excitation idea. Again, at low temperatures, all the electrons would be in this superconducting paired state. The arrival of an energetic photon will break initially a pair, or soon after that, many pairs will be broken up by that energy, and create excitations at a higher energy, which then will have an effect on the system in the following way. The superconductor is patterned into a strip. The strip is approximately a quarter wavelength at the microwave measuring frequency, and the strip has a magnetic inductance which feeds into making it look like a resonance circuit near the quarter wave length of the strip. And that inductance consists of a term which reflects the kinetic energy of the moving pairs, not of the single electrons, but of the moving pairs. So if we remove a number of pairs, we will decrease the number of pairs, we will increase this inductance, and by the laws of electricity and magnetism, reduce the frequency at which this is resonant, and that's read out in a microwave measurement which uses at room temperature some special purpose but relatively conventional electronics, and can be made into arrays of thousands or probably tens of thousands of devices, and maybe even more. This is a very promising way for doing arraying, and the microwave idea of using different frequencies to address different devices, different pixels, is an important advance in this field generally, and can be used also for reading out the squid magnetometers that I talked about earlier. So this is a great new development. Here's a picture of one of those devices. It's not a picture really, it's a drawing. And the high-frequency photons, in this case, again, photons that are millimeter wave, like were shown in that radio astronomy observatory, come in on a strip line. They dump their energy in this end of the resonator, which is that long, and this is the through line that reads it out, the green. So everything here that's green or red is niobium, and these detectors have already proven their operation, and now they're being refined for large-scale applications. Now, this is a point at which I'd like to emphasize that this field has been both collaborative and friendly. That may be a tradition among astronomers, but certainly it's been very satisfying to be able to learn from colleagues, to share advances. And the group at UCSB has started a venture of an open source approach to the room temperature electronics to build on the large available and soon to be available commercial microwave systems. And that is a notable advance in the field because it provides a lot of leverage from the other areas of microwave and circuit development to be used in this venture. So I'd like to thank my colleagues, and I think all of us feel indebted for this very good collaboration mode that's been going on in this field for quite a while. And it was established early on by a number of the senior people who started back in the 1970s and 1980s doing this kind of work. Well, now I'd like to turn to the photograph that is on the poster, and that is from Dr. Adriana Lida, who's at NIST. And I'm turning now from X-ray detectors to detectors of visible and near-infrared light. So we're going down about a factor of maybe 1,000 in the energy of the photons. So the signals that will be generated will be smaller. This is a case of a thermal detector, a TES detector. So we're back to the bolometer and calorimeter that I first talked about. And there have been major advances in the efficiency of coupling in photons In the old days, the same absorbing material, a tungsten layer, which is a good superconductor at very low temperatures, absorbed about 20% of the photons at this telecom wavelength of 1550 nanometers. By putting a reflecting cavity behind it and a quarter wave coupler in front of it, all using thin film techniques, the efficiency has been boosted up to 95% with still fast response, and this has been recently integrated into a fiber optic coupler so that it looks very much like an industry standard piece of apparatus, but one that works at 200 millikelvin in ultra cryogenic environment, but is all fiber coupled and can then take in photons from room temperature. And this is a picture of 4 of those devices, 2 that are the size that gives this performance, and 2 that are somewhat larger that have somewhat less resolution, but a larger absorbing area. Okay. Now, those detectors are fast because they have a microsecond response. That's also because they're smaller than the X-ray detectors. But this is not as fast as is desired in a number of sort of on-the-Earth applications, although this would be a very good detector and will be a very good detector for studies in quantum information physics. One of the detectors that looks extremely promising is called the Superconducting Nanowire detector. And this consists of just a meander pattern of superconducting metal. The light is metal. The dark is the substrate that's not coated with metal. This is a microwave transmission line, and this device would sit in its superconducting state. When a photon arrives, it will drive a small section of it non-superconducting, but because that small section is in series with the rest of the wire, the entire wire will have a finite resistance, and that's what's measured. Oops. Let's see. I want to get rid of that. Okay. The work I'll describe is done at the MIT Lincoln Lab and in collaboration with a group at MIT. And this picture is from work at Yale, but the work I'll describe has been honestly more successful and uses a different material, niobium nitride. We explored niobium materials here. And the niobium nitride detector is built in a slightly different fashion. It's built on a sapphire substrate, but because the material has to be deposited at very high temperatures to get good quality, it sits on the back of the substrate. An optical cavity is then applied back here. The incident photons come from this side. The anti-reflection coating is far away on the other side of the sapphire substrate. And so this isn't quite as integrated as the one I showed on the previous slide, which is a TES, but it has some wonderful behavior. The types of experiments that they're doing is in quantum information science. But first, let me show you the detector structure. This is a 19-inch rack. Here is the refrigerator part. There's the compressor that cools it. These devices do not have to be ultra cold. They have to be somewhere between 2 and 4 degrees above absolute zero, 2 to 4 Kelvin, which is a much less expensive and easier to use refrigerator. Not trivial, but certainly since everything is fiber coupled and comes out to room temperature, the user doesn't have to get involved a lot with the cryogenics. And a typical device might be a meander pattern where there are actually 2 meanders, a left-hand one and a right-hand one, which would measure the 2 different states of the incoming photons. For example, polarization would be one choice of 2 states, of the 2 states. Now, the devices are not as high efficiency in terms of their detection as the one I showed from Dr. Lita, but are good enough to go and do some very nice experiments. The experiment that's been focused on is called quantum key distribution. Some of the world's experts on that, including Se-Ru Nam, are here in the audience, and I will defer detailed questions on that to them toward the end. But in any case, the main idea is that in distributing a quantum key, you want to know if someone has snooped on you. If you do it at the single photon level and you have enough information, you can tell if one of the photons is missing. And if all the photons are there that should be, then presumably the distribution is secure. That's my cartoon layman's understanding. And so you want to be able to measure single photons with good efficiency. Now, the choices for distributing quantum keys in reasonable cost would be not to build a whole new network, but to send them at the usual telecom wavelength, 1550 nanometers, or possibly at 1300 nanometers, where the fibers are relatively transparent, not as good as 1550, but you avoid the traffic and possible interference from the regular traffic. Okay. And here's a result. I'm using a slide from Eric Dollar at Lincoln Labs. And this is a somewhat earlier, very successful result demonstrating that one could communicate at a rate of over 10 kilohertz, a distance of 100 kilometers, a little bit over. And the 100 kilometers is taken as sort of an industry standard. That's the distance between fiber huts where you would have either receivers or repeaters. And that is sort of the standard length that is required, although certainly many of the applications may be over shorter lengths. And a recent result from the MIT Lincoln group goes much faster. This red dot should agree with the red curve. And the reason that I'm told that it's a little bit below is for the red curve, they used the parameters that they thought the device would have. The actual parameters are slightly less, so it's slightly below the predicted performance. But in any case, things are appearing to be both well understood and advancing to the point that this would be an appropriate thing to implement when you need very high security. This is a picture of the first experiment that I described from Se-Wu's group. Now, this has gone into a real application, and in the Geneva Elections, they used this distribution of the quantum key to allow communication between the data center that would count the votes and presumably, the data center that would munch on things and the central voting counting station. And the thing that's notable here is that the distance over which it was done was 4 kilometers. You might ask, did they use superconducting devices here? The answer, unfortunately, they didn't. Well, they didn't have to. ID Quantique, which is a Swiss company, has been very successful in fielding some of their initial equipment for this type of application, especially, and not surprisingly, in Switzerland. And so, just like the state of Connecticut supports United Technologies, and I'm sure California supports many of its industries, quantum communication is a big thing in Switzerland, and indeed, this is now an accepted standard procedure for Swiss elections. So there is a real-world application. Now, over 4 kilometers, you don't need to have the outstanding performance that would be achievable with the superconducting detectors. So the indium gallium arsenide avalanche photodiodes, which are part of this company's repertoire, are what were used. Okay. Now I'd like to go to some applications that we haven't heard about in our workshop that I have some knowledge about, but I'm not a world's expert on any of these, and yet I thought they would be fun to present, especially to the community that's in the workshop, which is primarily not biologists. Okay. Now, I said that one of the motivations for single photon detectors is you would like to be able to measure small signals, and single molecules certainly don't emit large signals. And indeed, one of the characteristics is many of these fluorescent molecules emit only thousands or tens of thousands of photons before they die. The mechanism of death is usually something happens when they're in the photoexcited state, often with oxygen. And so even though in theory they should be just living forever, in practice the fluors die. Now, that means that there are only a finite number of photons to collect. You obviously want as efficient an optical collection system, but you also want as efficient a photon processing system. And so instead of using dispersing gratings or other types of filters, you would like to be able to measure every single photon and get the spectral information for every individual photon with the single photon detector. Now, an example of an application is shown here. Oh, and most of these biological applications are done in the visible and the very near IR. Almost all the equipment is commercial, which means not superconducting. They use single photon avalanche detectors quite typically, except in the mid-visible when photomultipliers are used. And this is done worldwide in thousands of laboratories. Okay. Also, typically these are not imaging applications for the single photon level because they're using confocal microscopy, which focuses down to a point and then might either sit looking at one molecule or translate across the sample and look at lots of different areas sequentially. So how does this work? Well, one of the techniques that's used is called FRET, fluorescence resonant energy transfer, or Forster resonance energy transfer. And this one is something that is sensitive to the calcium concentration. And the example would be the following. Imagine we have a blue fluorescent molecule and a green fluorescent, or a yellow fluorescent molecule. So this is yellow fluorescent protein and cyan fluorescent protein. Okay? Or something else that fluoresces in those two colors. Input photons at an even higher energy, a somewhat shorter wavelength, will make this fluoresce in the blue. And if this one is far away, it won't fluoresce at all because this input photon doesn't match its input requirements. On the other hand, if the excitation comes in and these two fluors are near each other, by transferring in the near field, the energy will be transferred to this fluor, which will then emit in the yellow-green. And so in the closed state, it will be emitting a different color than in the open state. And if the opening or closing depends on the calcium concentration, this is for the higher calcium concentration, you can actually measure calcium concentration with this fluorescent technique. Okay. Now, that's typically not a single molecule measurement, but it gives the idea of how FRET works. Okay. Here's an example, and this is just taken from the web. It's to, again, just show the example and that you follow these things in time. This would be the count rate in the red channel and the green channel. And the color here is just labeling which channel it is. And so when it's in the closed state, it's mostly red fluorescence. You're illuminating it with some slightly higher energy photon. When it's in the open state, it's much more green fluorescence and very little red fluorescence. So you could follow whether a single individual molecule is open or closed if it's tethered on a surface, for instance, with a biodin-streptavidin tag that holds it down to a surface. And that's actually what I'll talk about next. But you can see you can follow this because of thermodynamics, it's sometimes open, sometimes closed. You can also go to situations where once it closes, it stays closed. For example, and this is something that the original work was developed by Dr. Paul Lizardi, who's presently in the Yale Medical School. He did this at the New York Public Health Service. And although this is a cartoon, it actually represents rather accurately what's done. To start, DNA consists of a double-strand structure. Each strand consists of a backbone with base pairs that are either C, T, G, or A, and the A likes to bind with a T in forming the double strand. So this would be a single strand. You can buy that. You can get it shipped to you by FedEx. You can specify the exact sequence you want, the exact length, and you can order it and get it 2 days later. I found that amazing when I first learned about this, but it doesn't amaze the biologists. And in fact, most major universities, including Yale, have their own synthesis facilities, so you can get even faster orders done. Now, imagine that you're in solution, or that this thing is held in a fixed position, and this is the structure you want to look for, and you know what sequence you want to find. Imagine that the complementary sequence of these single bases has already been designed, and that you order from your supplier a structure that has a green absorber, a red floor, and a black dot, which is a quencher. Now, the quencher is a molecule that just gobbles up the energy in the near field and does not let the green transfer its energy to the red if it's nearby. So it just is a photon gobbler. These things exist. You buy them commercially. The initial structure is called a hairpin because these are base pairs where the bases that are here are all the complement to the bases that are over here. So imagine that this thing isn't around. It likes to stay zipped shut, and there's enough energy to keep it closed that thermal agitation doesn't break it apart. So it's stable at room temperature in solution, and if you shine in light, you don't see any glow of fluorescence. Okay. Then you introduce this structure, which over a length of it has the complement to these bases over here. It slithers around, it sort of marries together, and because it likes to form a structure that's not completely closed, it doesn't like to form and then have the ends hanging out, you get many more bases bound together, and it pulls apart the zipper. So you might have 12 here and 5 or 6 here. 5 or 6 is enough to keep it together if it's by itself, but the 12 will win out energetically, and after a short while, you will find that the red floor lights up because the quencher is now more than 5 nanometers away. If this sounds like science fiction, it isn't. This is in routine application in many biochemistry labs in the world. Okay, and it all started with the simple sort of cartoon picture. Paul Lizardi did that. Now, where could this go? Well, it's clear that this is something that could be sensitive at the single molecule level, and I've seen these things done, tethered to surfaces, and you can actually expose them to solution and measure very low concentrations because these things sort of collect from the solution. But to think about it, if you had knowledge of what a cancer molecule or single strand would look like, you could then essentially paint this on or take it into the body if it's non-toxic, and it would light up when it got there. You could then do something else. You could attach another piece that would be a drug releaser that might be released through some other photochemical application. So you could actually then say, go and target the cancer locally. So it's not chemotherapy, it's a very local therapy. This is not, it may be fantasy today, but it's the thing that many of the people in the cancer field are thinking about, or related targeted approaches. Another idea, and this is one being pursued in the Yale pathology department, is the surgeons who do remove skin cancer, head and neck cancer, have told us that often they have to remove much more tissue than they think is cancerous just to be sure they've gotten it all. If you could take some of this stuff and simply paint it on during surgery, instead of having to send something out to the pathology lab and get a result back later, in real time you could be monitoring if you'd taken enough away. This would be a marvelous thing, and in the appropriate photon energy ranges, which is probably in the near infrared, this would be a very exciting development. Okay. A completely different area is laser communication, laser ranging. There are many exciting things we heard about very long distance communication through space at the single photon level in the workshop. I thought it would be fun to cite something that's up there circling us as we speak and was launched a number of years ago. This is a satellite, the Ice Cloud and Land Elevation Satellite. It's that one. Slides from Goddard Space Flight. And this was actually launched in 2003. It has a moderately powerful laser that's at 1064 nanometers and measures reflection from the surface at that wavelength, and also measures the scatter back from aerosols at half that wavelength. The photon modules are from commercial vendors. I'm sure they were somewhat specially developed, and infrared enhanced silicon APDs for 1064, and a picture of what it looks like actually in its initial orbit collecting data. So this is a real application in environmental things that's an important single photon application and uses detectors that do exist. I'd like to close with a very futuristic jaunt going back to space astronomy and invoke a motivation from our colleagues that have been provided at JPL, Dr. Boris Karasik and his research group. If one wants to observe at photon energies that are much, much lower, much of the transmission of the photons is, the medium is much more transmissive. There are relatively few background photons, and with a high-resolution instrument, you might have the background arrival rate of photons in the range of 100 per second. And if you were looking at a narrow emission line from a molecule that had an intensity of maybe a few hundred or 1,000 photons per second, this light blue, it would stick out above that background, but you would need a photon detector that was extremely sensitive, much more sensitive than anything that exists today, or at least anything that's been fully demonstrated today. How could we make it? Well, the most sensitive detector of photons in this milli-electron volt range is actually provided by semiconductor quantum dots, which integrated into an ultra-low temperature transistor were able to detect photons in this range, but had a very low detection efficiency and only accepted a very narrow range depending on how it was manufactured. So it doesn't have the flexibility to have the appropriate performance in the astronomy application. Okay. We've been studying at Yale a concept that Dr. Karasik and colleagues have pursued of having a very small transition edge sensor made from titanium in an antenna, so the antenna catches the photon, which is much, much larger than the small titanium volume, and then heats up the titanium a tiny bit. Karasik's group has had initial success in measuring photons of somewhat larger energy. That's very recent. But we decided about a year ago to try a way for testing these things that was new and would allow us to get the testing and maybe iterate on device design, on the signal processing, on the other aspects of performance. And the idea is to send in a pulse of microwaves, a short pulse so it happens quickly compared to the response of the device, and then watch the device heat up. And if we average the device performance, we can see the response shows on a few microsecond time scale the expected response. In fact, very close to expected. If we send in a single one of these pulses, it's much noisier, but we can still extract data, and it's approaching the performance that would be needed in the future space application. Of course, this is not a real photon. This is a fake photon. We've given it a name. It's called a faux photon or a photon. Some of you may follow the show The Pink Panther and recognize that that would be a word that Peter Sellers would use. And where this would go is in an ultra-cold dish, maybe as big as the one that we saw at the beginning of the talk, in this ultra-cryogenic housing over here, surrounded by a cooled light shield behind it to keep background light. And this is one of the future challenges, and I hope I'll be working hard at this for the future years, and we'll see it come to fruition. Thank you very much. And I think we'll bring the lights back. Okay, so take any questions there may be. Okay.
What count rate do you think your visible sensor could give?
Okay.
For the PREP sensor.
Okay, so the question is for the visible sensor in near IR, what count rate is possible? And I won't answer for the APD, which is not my field, but rather for the nanowire detector. Present count rates are in the range of 100 megahertz. That is not an energy sensing detector, it just goes click. But put with a color filter in front of it, that would be fine. And although that's sitting down in the cryogenic system, it's fiber optic coupled. Okay. And so that could, I think, with design be pushed a factor of 10 faster. And if you had a bunch of interleaved wires with multiple amplifiers, not 100, but maybe 5 or 10, you could get the count rate per area, and that's for a 1 pixel thing, even 10 times faster. So really, really fast. Okay. Probably faster than present room temperature electronics could gobble it up, but that's someone else's venture. Okay. Any other biological questions? Okay. I would, yeah, sure.
Talking about the doctor painting on the stuff and seeing if the cancer has gone beyond the perimeter. You gave that as an example.
Or if the cancer has been, if there's any cancer remaining after they've excised.
Is that realistic in terms of photon counting in a clinical condition where there's a lot of background light thing, or is this something you see could actually happen?
Oh, I think you'd have to have pulse laser, time-gated detector, maybe tricks with narrowing the line width, etc. It's such a big payoff that I think they will stand on their heads and make it work if the detectors are there, if the fluorescent molecules are there, if the recognition sequence is there. My understanding is that none of those are ready, but that the recognition sequence is the one thing that's really the uncertain thing. The others are technology development issues. That's my layman's understanding of that. Okay. I would maybe ask if we could get any expert comment on the quantum of either Sewu or Alan or any other experts on quantum key distribution and where you see those applications, sort of who wants to pay the bills and how soon, as much as you might wish to say.
Well, in addition to the quantum key distribution...
Oh, and this is Dr. Alan Migdal from
In
NIST.
addition to the quantum key distribution is the idea of quantum computing. And that's something that really wants to have single photon sources and single photon detectors with very high efficiency. And the payoff there, if it works, is it allows you
they refer to an exponential speed up in the computing capability. Currently, we have Moore's law doubling every 18 months, something like that. Projected to hit a brick wall when you can't make transistors smaller than an atom. The use of quantum bits instead of classical bits, which can be in the state 0 and 1 at the same time, allows for potential massively parallel processing, and would make Moore's law look like the current interest rates you get at the bank.
For those of you that have checked.
It really requires efficient sources and efficient single photon detectors. So at the moment, that's who's paying the bill.
Okay, so maybe what Dr. Migdal is saying is I've only talked about half of the big problem. That's okay. It's a big half. Toon, did you want to?
Yeah, I was
Toon Klopvik from Delft University.
So how soon will you expect that this technology will be used in the U.S. elections in Florida like they have done?
I see. That's a question from an expert. Okay. Okay. I would like to ask for two other expert opinions. One from any of the representatives from the non-superconducting detector community to say a few words to sort of moderate or add to what I've said. And I'd also like to ask Professor Zmudzinis to comment a little bit more about the kids that have been developed, because that seems to me a very exciting development that I've been following, but I'm not the expert on them. So would you like to say something about photon, non-superconducting things and the excitement there?
As you go to the applied, this is all future, but in the X-ray, in the UV, where the photons have a little more power, we've been doing photon counting for a long time. And so there's a lot of astronomy based on counting the photons and counting vectors, because they are so easily, in a way, effectively easily detected, because they come in and knock out an electron. It's not pushing photons. So a lot of what you're talking about is sort of the optical, infrared, far infrared, even down to the that's what's so amazing about this stuff. You're eventually taking the capabilities of what we've been using in X-rays for a long time and pushing them down to the other way.
Right. So maybe a related way to say that is if you use semiconductor or metal structures, the band gaps and energies you're talking about are in the electron volt range. If you use superconductors, the energies are either the thermal energy or the band gap energy, both of which are in the milli electron volt range. So you get much less granularity, and that's one of the reasons that the superconducting detectors have the wonderful performance that they do have. Okay. Jonas, could I put you on the spot to say a few words about the MKIDs?
Well, I think we'll be hearing about those detectors a little more.
Right, but for the people who are not at the workshop.
Probably tomorrow and Thursday. That's a project that we're working on quite a lot here at JPL and Caltech. My personal interest is to develop detector arrays for the submillimeter and far infrared wavelengths. One of the really excellent things that, in my opinion, Andrew Lang did as our division chair was to hire Steve Payton, who I see sitting in the audience.
Could you raise your hand?
Steve has come to us from University of Chicago, where he was working with John Carlstrom to build the South Pole telescope. It's a 10-meter telescope, as you can understand from the name, located at the South Pole. So quite a challenge. So that was Steve's warm-up exercise for the next project, which is very large telescope at 18,000 feet.
Bigger than this room.
Yeah. Now, one of the first things that Steve did when he got here was he looked at the telescope design. He said, "You haven't done this right. You could have a field of view that's a degree instead of 20 arc minutes. And by the way, where are my millions of detectors I'm going to need to pay that focal plane?" So that's what we've been thinking about. How do we get millions of detectors ultimately in the camera that would operate on this telescope? And so obviously cost per pixel is a huge driver. And that's why we're particularly interested in the kinetic inductance detectors. It looks like a way to really bring the cost down, the cost per pixel, to the point that we could really afford the cameras that have millions of pixels of these superconducting detectors. So we think we have ideas for how to do that. And in addition, through work done by our colleagues at JPL, Rick Ledoux and Peter Day and other people in the superconducting device group there, we now have a beautiful new tool, a new material, titanium nitride, that seems like it's going to offer us energy resolution that will be pushing to single photon sensitivity in the far infrared. And so that's another thrust that we'll be following on. But you'll be hearing, well, the people at the workshop will be hearing about this more over the next few days.
Thank you. I'm told that the pizza's here. I want to thank folks who've done such a nice job organizing. Thank you very much. And if you'd like to take a pair of glasses with you, enjoy them. It's a gift from the Yale Outreach. Donations are happily accepted. And I'm sorry?
They're good with fireworks.
They're great with fireworks. And also, one last suggestion, a little bit dangerous. So undergraduates, close your ears. If you take a pickle and connect it to your electrical socket, it will first hiss and sputter, and then it will light up. And if you look with the glasses and you calibrate them, which you can do with, let's say, a low pressure discharge lamp, you will see that the pickle actually emits the sodium doublet. And you'll also be able to see on the web that there's an extensive literature called the electric pickle. And you will see that a lot of it was contributed to by people at Digital Equipment Corporation. Those of you older will remember that used to be a computer company. And the reason that they did it is apparently for the last 2 years of the company existence, they had nothing else to do. So they wrote scholarly tomes about the actual physics of the electric pickle. So go and enjoy, use your glasses, and let me know if you find anything new. Thank you.